Okay, I'm Ronen, Director of Product of the Aerospike Database. I'm also lead for Worst Dressed Speaker today, so vote for me later. I really want to go over what we've been doing, in the last year since last summit, and what we're going to be doing in the near future. So, Aerospike Database 6 just finished with the 6.4 release, and we're moving on to Aerospike Database 7, which is going to be a series of releases coming up soon. I wanted to just first quickly review what was the focus of Aerospike Database 6. So it was all about an operational rewrite of secondary indexes, right? Not massive changes to the developer API, but more making it easier and more appealing for the operations team to run it, right? So we started with some precursor work in Server 5.6. We had set indexes, the ability to just identify the records in a really small set that's embedded in a giant namespace. We used that structure that we developed for that as part of the memory reduction that 5.7 provided, right? We were able to cut down the memory cost of secondary index by 60%. 6.0 launched with a whole bunch of things. The biggest thing is kind of massively allowing for horizontal scaling of really large queries, right? So if we had in the past, we had the ability for scans to run against partitions. And where it came really useful is if you had a really large Spark installation that was pulling data out of Aerospike. So Aerospike is a data store, that's cheap, scalable, fast, all those things that Aerospike database gives you. And you're doing the compute in Spark. We had customers that were coming to us with thousands of cores. And if you have thousands of cores, at the time, the most granularity we could do was with scans was on a per node basis. So you would have your 100 node cluster, and you'd have a 4,000 core Spark that was mostly not doing anything, right? So we did scan partitioning a long time back, and we wanted to have the same approach for if you're doing secondary index queries, right? Because the idea is well, what's the difference? So this structure is, these queries can be done on a partition basis if you wanted to do a lot more in parallel and really separate the data into different workers. And that is used by our analytics connectors. It's used by AS Backup. You can take a parallel backup of a lot, on different, spin up a bunch of different client machines and take parallel backups to do it faster, right? It added pagination and tolerance of changes to the cluster. And we also allowed you the ability to designate a short query. And again, a short query is a term for, I have a very large data set, but I'm actually pulling, the result set is typically really tiny, right? So if you have a very large number of queries running at the same time, thousands or even tens of thousands of queries, not key value operations, but queries at the same time, this optimization on the application side allowed you to do it because it bypassed some kind of monitoring and did all kinds of other optimizations to be able to do more queries in parallel. And that's, again, used heavily by customers already. And then, we added the ability to index an entire namespace, which is useful for certain things where you're trying to not address specific sets, but just the whole thing at once. Another huge thing we had in Aerospike Database 6 was the ability to deploy on more than just secondary indexes in memory, right? So we allow you to designate secondary indexes to be in persistent memory. We allowed you to put them first thing in shared memory, just like the primary index. In the past, you couldn't do a warm start. If you had secondary indexes, those would just kind of evaporate if you rolled ASD, and then you needed to read it off the disk, right? So it really made for slow upgrades if you dared use secondary indexes. So we fixed that by, secondary indexes are in shared memory just like the primary indexing, so that whole warm start penalty goes away. We added the Aerospike shared memory tool that allows you to actually, if you shut down the node cleanly, to copy those things. So let's say you knew you're planning to roll the whole host machine, not just the daemon. you could just save those to disk and then recover them from disk for a much faster restart cycle. So in 6.3, we added the ability to put secondary indexes in persistent memory, which unfortunately is a technology that is dying, but still really awesome if you can get your hands on that hardware. And then the last thing is, in the last release, we added the ability to do secondary indexes on flash. So in theory, you can now have your primary index in memory and your secondary indexes on flash if you have a lot of secondary indexes and you feel like you don't have enough RAM in the whole cluster to do a lot more secondary indexes. Obviously, those things have an impact on write throughput and all that, but if you don't have, if it fits your use case, this gives you a lot more flexibility for deployment. There you go. On the developer API enhancements, the query API now is the same exact classes and the same subsystem on the server, whether you're doing primary index queries, which is what we called scans in the past, or secondary index queries, right? It's the same thing, which makes it easier for developers to actually write their applications. We're adding the ability to index blob data. Until now, you could only index strings and integers, right? So the ability to index blob data types is actually something we're doing for our graph database to get more efficient on their storage. They use a specific data model where the ability to refer to other records is more efficient if they just keep them as a blob and not like serialize them into something. And in the following releases of Server 7, we will have the ability to index maps, lists, doubles, all the other data types basically. We added the ability to match an expression to match whether an object that you have, a specific object, is what exists in a bin or some nested structure in a map. Because sometimes you want to model an object as a map, like as a complete thing. So we already have that ability to just say, like, does this record actually contain this map? We added the ability to get results from map operations back as a map rather than something like a list of key value pairs. So it just makes it a lot easier to write something where I want to get a sub map out of my big document that is expressed as an Aerospike map. We added the ability to batch anything. In the past, it was just batch reads. And now you can do batch deletes, batch writes. You can combine them however you want. It makes it a lot easier. Obviously, the previous talk is leveraging that ability. We removed batch size limits in the most recent release. Until now, you had this config that just said, what is the biggest batch do you want to do? I mean, obviously, having really, really large batches have a memory cost associated with them. But, we removed this kind of like annoying operational limitation. The next release, which is coming soon in just a few weeks, 7.0 will have the ability to have a default ETL at the set level. So you'll still have default ETL if you need it at the namespace level, but now different sets will be able to have their own default ETL, which is, again, a flexibility thing. Heads up on this next change for Server 7.0, we're going to Lua 5.4. The 5.1 that we have, that thing is expired or end of life a million years ago. And we felt like we maybe want to go to a place where you have A, 64-bit integers, and B, something that's actually still under support by the Lua community. So that's coming soon. Shouldn't affect you unless you're doing some really extreme things with UDFs, but just be aware. And then the big thing, of course, is all of this work is to make way for multi-record transactions. On the client and framework side, we've done a lot of work on Spring Data. I know not everybody develops in Java, and even in Java developers, not everybody does Spring Data, but that is still a very popular framework. A lot of our customers use it, and we've done a lot of work to move that to have parity with like all the feature sets that the raw client has. There's a new Rust client that is coming. That's significant for us internally because there's going to be a new generation of dynamic language clients, Python, Node.js, et cetera, that are based on the Rust client. So that's a big thing that's coming that will become official. There's a PHP client on the way. If anybody's still developing in PHP, let me know. We want to get feedback from you. Async Python client, something that's been requested for a long time, that's coming. And then I had to mention again, if you're a C# developer, you should check out the LinkPad driver. It's really convenient. In terms of operational enhancements, we significantly boosted XDR throughput in the 6.1 release and the 6.4 release. We're talking about like for any type of operation, you could get up to 100% throughput increase. So if you're doing a heavy reliance on XDR, I would suggest to just check out the new releases because there's like no downside to this. So the way it works, again, you can read the technical blog post, but it basically uses a partition affinity in order to use a lot less threads, use a lot less file descriptors, so there's a lot less connections actually to do more throughput. And that really, in a large system that does a lot of throughput, it also increases the stability by driving down these connections that we're doing to remote nodes. We've already mentioned this several times. We added the ability to run on, in AWS and Graviton, but that's basically, any ARM 8.2 compatible processor, so also it'll run on Graviton 3. We increased the speed of truncates. If you're doing a lot of truncate operations, it leverages set indexes if they exist. And then in terms of multi-tenancy, there's been a lot of things in the past and upcoming. There's storage quotas, right? So if you're separating different applications to different sets, you have the ability to do already like limits on how many reads and writes per second those users on those sets can do. We added the storage quotas, so you can limit how much storage they're actually using by putting a specific set limit. And then 7.0 is removing that weird unique bin names per namespace limit, which used to be 64K. Now you can just do whatever. That goes away. And we're increasing the number of sets per namespace to 4,095, okay, instead of like 1K. We mentioned this before, but this is like an initiative that's just going to continue to keep giving. In Server 6.4, we started moving towards integrating with other secrets management services through an independent agent that's running. So the secret agent already has integration with AWS Secrets Manager. GCP integration is coming soon, and then we're going to have Azure and HashiCorp Vault. So currently we have a tight integration in the server with HashiCorp Vault, but it's going to move into the secret agent, so you'll have that flexibility of moving between different services, or if you're deployed kind of cloud agnostic, you have certain clusters living on AWS, certain clusters living on GCP, you'll be able to, from the server's perspective, the config doesn't change, but you'll be able to locally configure the agent to use a different service in the background. And let us know if you are running on a cloud platform outside of like the big threes, right? Like if you're Alibaba Cloud or you're in IBM Cloud or whatever, just let us know. It's something that we can add later. The big thing coming in Server 7.0 is a complete in-memory rewrite. So I want to spend a little bit of time to talk about this. If you're purely in memory or you're in memory with persistence to disk, this is going to matter to you. So the real drive behind all of this is like prerequisite work that we need to do for multi-record transactions. Okay, so there was an ulterior motive behind all of this, but it still has a lot of benefits for anybody that's using an in-memory namespace. So in Server 6.4, we already removed single bin namespaces. So first thing, if you're on single bin namespaces or data in index, my apologies. We know that it's painful. It's only painful for you guys. Other people don't have a problem rolling into Server 6.4 or Server 7.0, et cetera. There's special upgrade instructions. You can take a look at them. Okay, so we tried our best to not make it painful, but unfortunately it's not the best if you're in single bin namespaces. Not a lot of people remain on single bin namespaces, but if you're using that, please read that closely. For everybody else, one of the things we got out of it is we reclaimed a bunch of index space. And that index space we're going to need to use for multi-record transactions. But there's other things that we can use it. For example, the 4,095 sets per namespace was just by giving some extra bits to that thing, right? Being able to talk to more sets that way. So what we're doing is we're unifying the storage engine. The storage engine, the storage format was already unified for if your data on persistent memory or data on SSD. In-memory was kind of like this weird outlier. So the main thing to explain the difference is on disk, we have one pointer from the index, right? And then it's just contiguous, right? The record is just basically written as one serialized unit, and then we just read it with a single read IO. That's part of like how Aerospike works so fast when it's data on disk. But in-memory was different. Every single bin is stored in a different location. So you have multiple indexes, and it has its own serialization format. So when you're writing it, it just works differently. So one of the things it gives us is when we have a uniform format, we can take the configuration that you have for data on SSD and apply it the same way to data in memory now. So if you want to use compression, you'll be able to do compression on your in-memory data. So just to give you an idea of what this means, if you have already compression turned on with in-memory persisted to disk, you already know what your compression ratio is. That's going to be exactly the compression ratio that you get for memory. So if you have a 0.8, meaning you save 20%, that'll be exactly the same for when we go fully in memory, because it's exactly the same storage format. Same storage engine, right? So you may already know what this is going to give you just by looking at the statistics for your persistence layer. The other thing is the ability to warm restart it, the data. So until now, an in-memory namespace, and I'm quite sure that means for any in-memory database, when you're restarting your server daemon, ASD in this case, or some other competitor that's in memory, that thing goes away, right? The memory is in memory. The data's in memory, it goes away, right? So now it's going to live on shared memory, and it'll work exactly like when the primary index or the secondary index is in shared memory. Meaning you'll be able to shut down Aerospike, upgrade it, right? Go from 7.0.1 to 7.0.5 if you have to patch it, and it'll just immediately, the data doesn't evaporate. So that's one cool thing. The other thing is the shared memory tool, ASMT, will be able to persist that. It'll be able to, if you did a clean shutdown, it'll be able to just copy your namespace data from shared memory to disk. So in theory, if you really feel like a cowboy, you don't have to have a persistence layer. You can just have fully in memory, assume that you're going to have a clean shutdown, and you'll be able to copy this. So before you roll the whole host machine, like you're upgrading the OS, you'll be able to like just save it and then recover from disk. So that's another cool side effect. The other thing is much better garbage collection for your data in memory. Anybody that has run into heap fragmentation problems based on JE-malloc, we're now moving to basically, it's using the same exact write block format like disk. So defragmentation that used to happen on the persistence layer, right? We had to read from disk. We had to clean the blocks that are on disk. Now they're mirrors of each other. So we can do that completely in memory. So if you're in memory, persisted to disk, and the persistence layer was causing back pressure, that goes away because they're exact copies of each other. Things like cleaning up durable delete tombstones, the tomb raiding process happens fully in memory. The defragmentation happens fully in memory. It's continuous, right? So you don't get this weird heap fragmentation issues. All of these things, we don't touch your disk for reads anymore if you have a persistence layer. It's only writes. So back pressure goes away as well. CPU should probably drop because we're not serializing in two different formats on a write. We're just doing it once with the same kind of very efficient flat format that data on SSD uses. Whatever goes into the write block size, the write block now, will now be, we only do it once. So that should also drive down CPU associated with this, unless of course you're doing compression and now you take back that CPU towards compression, but nothing's free. And the main thing is we're not doing this to torture anyone. It really is all about, it's a prerequisite for multi-record transactions. Okay, so I think I went pretty dense on the technical side. If you guys have any questions, I'm happy to answer those.
So what are the compression algorithms supported for the in-memory?
Same exact thing you have for disk. So Z standard, LZ4, and Snappy.
What are the operations that were impacted by the heap fragmentation problem, which you have solved moving away from JMalloc?
So the reason it existed in the first place is that, just because of the way JMalloc allocates memory, is we try to write things back into where they were. But if you do a lot of reads and writes and your bins are constantly changing, you can't fit it. So you already allocated a certain amount of memory, now the bin is bigger, you got to actually allocate it somewhere else. And we don't have any control over the garbage collection of JMalloc. So this gives us full control, right? In general, any system that's tried to go for performance and throughput, you want to have as much full control over these things, right? One of the problems in some of the competitors is that they're, written in Java, they rely on JVM, you get this garbage collection cleanup that's completely out of your control. And you can tell people use a different JVM, but it's pretty annoying as a database to not have control over these things. So our defragmentation happens now exactly like it's on disk. Continuous defragmentation is one of the reasons Aerospike doesn't have latency spikes when your data on SSD. So it's the same exact approach. We literally using the same storage engine to defragment your memory, and we're quite sure that it's going to perform massively better and not have these memory growing until in some extreme use cases, you need to restart the node. So that kind of goes away.
Sure. Sorry, I have a follow-up, a quick question. So what I wanted to ask is the fragmentation problem in heap has been seen in one data structure over the other more? Was the problem aggressive in one of the data structure than CDTs, something on that front I wanted to, or is commonly seen everywhere? Yeah,
well now it doesn't matter because we now do reads and writes and clean up in write blocks. We're kind of agnostic of the data. So the data structure is not going to change anything. In the new format, starting 7.0, it's not going to matter what data types you use. It's just going to be, it's just going to work because we just do defragmentation of blocks. So that problem goes away.
Sir. Any encryption technique used in JMalloc?
I'm sorry?
Encryption technique.
Okay, so encryption in this case is not going to happen in the shared memory. It still happens on the persistence layer. So if you're in memory with persistence, the encryption happens on the write to storage. And it's kind of like a choice, right? You get to choose if when you shut down a node, you want to nuke the shared memory, right? So it's IPCS command to nuke it. So depending on what requirements you have in terms of the encryption of this, you'll be able to control whether you want to keep it around or not keep it around.
Okay, thank you.
So multi-record transaction looks like a next big thing, probably in the newer version. So I just want to understand, is there some specific use case for which probably, because it seems to be a big effort, right? Or it is just because the other flavors are supporting it and we should also do. So
well, first thing, everybody has some feature envy. So I can't say we don't have that, but the main thing about it is, and by the way, doing multi-record transactions in a distributed database is an extremely difficult problem. right? It's very easy to control atomicity where you one machine, like old school RDBMS design, and it's like the way you scale is just bigger iron. It's still one machine, it's just bigger. So it has a unique set of problems, but no, it's, for example, our graph database, right? Our graph database, you want to actually, to do things correctly when there's a lot of concurrent updates, you want to do reads that then send you to more reads, right? So you do a set of reads and then you do a batch read for more data, and you kind of progressively decide, I'm going to do n number of, maybe 2 deep from this point on, right? You want to do this under one transaction if you have a lot of updates, right? So we don't want to be special case. So currently we have workarounds to deal with it, but they're expensive. You've got to do a lot of coordination to avoid situations where you're reading something that is incorrect because updates happened in between those 2 reads. So we can get more efficient by using the multi-record transactions. The other thing is the previous talk that was mentioning adaptive map. Let's say you have a really large record and you want to split it, because there's a reason we do write blocks. It's all about how does Aerospike compete in general with an in-memory database when it's serving from disk? Well, we do a lot of optimizations around what is ideal for reads and writes for the disk, right? We strive to drive down write amplification and really just reduce the amount. There's obviously that gap between application as a logical thing and the physical implementation of it is different, right? The reason we do 64 bytes in index is because of cache line efficiency, right? So there's a lot of ways Aerospike gets to perform as good as in purely in-memory database, even though it serves out of disk, because we care about these low-level things. So one of the things around it is we have write block size. What if your data is 20 megabytes for this one outlier? It's a corporate credit card, and you want to take all of the transactions for the one credit card for 10,000 people. So it becomes, you do have these outliers like TransUnion talked about. So when you need to split up that record, that's when you want to have a multi-record transaction. You don't want to adjust some header that points to all the children, and also, what if the cluster then fails exactly in between these 2 writes that you need to do, right? So multi-record transaction is very useful for realistic, things like that.
Thank you.
Yeah, so another question here.
Oh.
Yeah, so nowadays, like in SSD, right, 3D NAND flash SSDs are coming off with from 64 layer to 120 layers. Have you seen any performance gain on your 7.0? Have you tested it?
So we don't do as much drive testing as we did before, but they tend to use our tools. Like the manufacturers, a lot of times, for example, would use ACT. They'll use, FIO, they'll use ACT to try those things. I don't know specifically about that. I'd like to talk to you after about it, but on a whole, what's crazy to me is like how much improvement there has been in the hardware, right? So when Srini started this, there was a gamble on SSD technology. At the time, when I joined I joined after the company started. I'm here, 9 years, but we've been around even longer. SSD technology was super slow and super low. The durability was a lot lower. The cost per gigabyte was a lot worse. Even if Aerospike never put out another version, you guys deploying it would have run significantly faster and cheaper over time, just because of the hardware. So just like in-memory databases are kind of like evolved when when DIMMs used to get like cheaper and denser and cheaper and denser until they hit the physics limit of like how much dense you can get, SSDs still don't have a limit yet. So the hardware is constantly improving. Like when it comes to ACT scores, when I joined, the fastest drive was 70x. Most of them were around 1 to 4x. Now, multiple people have around 100x or higher. So that's just like an apples to apples idea of like how much faster they are. The durability has gone significantly. The cost per gigabyte is lower. Density, you have EC2 nodes that are 50 terabytes. It's pretty common now. It's not even that crazy. So it's all cool. I don't know about that specific technology, but we rely on the fact that they're also doing a ton of innovation. There's a ton of competition, and we do our part. So.
Okay, got it.
Hello. Yeah. So my question is also on multi-record transaction. So how would this be supported in case of when the records are in different nodes, right? And
Yeah.
second part to it is, since you said it can support multi-row transactions, can it be used for payment systems? So specifically referring to the asset
So
part there.
currently people already do payment solutions based on Aerospike because of the fact that we have strong consistency options, right? You can choose AP or CP for your namespaces. So a lot of people do it for the single record transactions, right? We give you linearizable reads. Dream 11 uses that. That's an example. But multi-record transactions will require, obviously, coordination. Like, we'll have something that is able to take the fact that, like, okay, I don't want to get too much into the implementation of it, but it has to do with observing the state of the cluster and being able to restart things. And, like, it's built on top of strong consistency, right? But it just needs to apply now to multiple nodes and multiple records. And, yeah, I mean, we've gone through 2 engineering summits, like getting all the core engineers together to talk about the implementation details with months in between to like reassess. We feel pretty good about it, that we can do it and do it well. Of course, there's going to be a performance cost. Like, it's not like you can expect to do, you know, start, do whatever you want, and then commit, and it be the same performance as a single record transaction. But, you know, if you use it sparsely for places where it's important, then you wouldn't need to do things like all those workarounds they had to do for adaptive map. We'll be able, for example, to make a version of adaptive map that just uses multi-record transactions and really simplifies a lot of this coordination code that you got to shove in there to get around it right now.
So any numbers on the latency? Would it be very high or manageable?
Latency is going to be completely dependent on what you're doing, right? You know, again, in an RDBMS, when you do begin and then commit, you can have one thing or you can have 100 things in between. And it's the same thing. It really depends on how crazy you want to go with this. There's obviously a progressive cost to latency because you've got to lock more things. You got to deal with more records that all have to be in this, monitor their state. You guys can find Sunil and harass him on the break. He knows a lot more about the implementation than I do. I write JIRAs. I don't implement, you know.
So you had this question here.
Yeah.
You in 7.0 you mentioned that you have changed the in-memory storage engine and the on-disk storage engines to be the same.
Yeah.
So my question is actually to ask, what were the specific reasons, if there were any, that the 2 engines were actually different? Why did you have a different in-memory engine versus ask the boss?
Blame that guy. I don't know. I mean, I think I joined when they were already separate. So I'm going to feign innocence. You know, sometimes you obviously, like in any system, it's iterative, right? If anybody, you know, if we were old school, if this was a nuclear bomber, then you would have serious product developers with a waterfall model, and it would take 20 years, and then it would be perfect, roughly. But like software, you just go quick, right? It's a startup originally, so.
So let me give you an answer to that. One of the things about, I think when we wrote the original code, we had written the in-memory thing separately because we thought that would be faster because we didn't deal with the defragmentation and all of that stuff. And then we added, I would say, the shared memory component, which we only did for the index, the in-memory index in HMA. So it's an evolution. There's no specific, we never got around to it because most of our deployments were in HMA. In-memory, there were not that many, and it was working well enough. But when we started going to multi-record transaction, what we realized was we needed to free up some space in the index of various things in order to make this happen. And so we identified this several years ago that this problem existed. So we just taking it as taking an opportunity to do it. So in memory, strongly consistent multi-record transactions will work well also, not just the HMA ones. So, I mean, so it will not be as durable as HMA, obviously, because it will not be in flash. But then you can use the case safety concept of having multiple copies. Maybe you keep 3 copies or 4 copies, and then run everything in memory. It's something which VoltDB does. So the way to think about it is these are all concepts, and then you have to decide how far you want to go in your product. That's all.
Thank you.
Yeah.